Yeah, okay, now we're going to start looking at some of these special rational functions which have what we call slant asymptotes. So we begin by looking at a simple one. X plus 1 over x. Okay, now this is a rational function, even though it doesn't look like one, but because it doesn't look like one means it's not written as a polynomial of a polynomial. But in this form, it's actually kind of easy to get an idea about the end behavior. If we let x equals 100, then we got 100 plus 1 over 100. So we got 100.001. If it's 1,000, we got 1,000 plus 1,000. If this x is a million, so then we got a million plus 1 millionth. So, you know, as the x values get larger and larger, this 1 over x expression becomes insignificant, okay? And for all intents and purposes, can be thrown away. So what we're saying then is, as x gets larger, the 1 over x here gets so small that it can almost be discarded, so that the function is going to mimic that of y equals x, okay? And that is, its end behavior is approaching that line. So the asymptote in this case is what we call the slant asymptote. Now, if we were to write this in a more familiar pattern of rational functions, then we would put these on a common denominator, and that would be expressed in this sense, and then joining together in the numerator, we would see it in a more traditional rational function format, and easily identify that there's a vertical asymptote at 0, and there's no x-intercepts, okay, and there's no y-intercepts, and the power in the top is greater, which is indicative of that kind of slant asymptote. So here's the slant asymptote. That's the line y equals x. We said as x goes to infinity, the graph is going to go towards that line. And you might also reason that as x goes to negative infinity, it's going to go towards that line. Okay, so and we're also going to be having to be constrained by the y-axis as the vertical asymptote. So here's our graph. Okay, here's our vertical asymptote as the y-axis, and here we are moving towards the slant asymptote. The slant asymptote. Again, we won't know like how high this point is or how low it is, how high this one is. Okay, again, that's the calculus which will find those things out for you. So let's look at some other examples. Okay, here's one. Again, immediately looking at this, it's a higher power in the top. If looking at it from a rational function standpoint, we obviously can see that we're going to get 2 and negative 2 causing the numerator to zero out, which contributes to the x-intercepts. We're going to have a vertical asymptote at x equals 0, and we could clearly just divide the numerator by this and get x minus 4 over x, okay? Which again suggests that as x gets very large, this 4 over x expression can, for all intents and purposes, be ignored. And so there our asymptotic behavior is going to move towards the line y equals x. That's what we're calling our slant asymptote, okay? So there's our slant asymptote. We've got again, the vertical asymptote at along the y-axis, and we've got intercepts at 2 and negative 2. So you should see that this would be the shape of it. Okay, clearly moving towards the slant asymptote, and then clearly moving towards the vertical asymptote, passing through negative 2, clearly riding along the vertical asymptote, passing through 2, and then heading for the slant asymptote. Here's another slant asymptote as type rational function, which is always going to be identified with the higher power in the numerator, and that's more specifically the degree of the numerator is going to be 1 power greater than the degree of the denominator. If it's more than 1 power, well, we'll talk about that. That means you'll have some other kind of asymptotic behavior. Okay. Easily we could see x goes into x squared x. So this would by simple division would be x plus 3 plus 2 over x. And the 2 over x, for all intents and purposes, can be discarded. So our slant asymptote is going to be the line y equals 3. Numerator factors to reveal our x-intercepts at -2 and -1. And here we go with the graph. Again, we've got the vertical asymptote at 0. So we're moving along, following that slant asymptote, going through our 2 x-intercepts and heading back down to right along the vertical asymptote. Over here, similar behavior. Again, these turning points are not going to be known until we study the calculus. This is a binomial having to divide into that trinomial. And this is going to have to be done through long division. So we're going to show you that long division right here. That is x plus 4 into x squared minus 4x plus 4. Again, we have to account for all powers, but since there's none missing, we don't have to fill in any 0 coefficients, but bear that in mind for other problems. X into x squared goes x times x is x squared, x times 4 is 4x. Subtract -4x minus 4x, -8x, bring down to 4, do division again. So this expression will rewrite as x minus 8 plus 36 over x plus 4. And really, again, moving towards infinity, that remainder expression, 36 over x plus 4, is pretty much ignored. For all intents and purposes, can be ignored. So we can get out of this our slant asymptote of x minus 8. So, and here comes our graph. Of course, there's our line x minus 8. Okay. We should agree that our y-intercept is going to be 1 right here. Should agree that our x-intercept is at 2 with a multiplicity. So you'll see that you only touch there 2. So it has that multiplicity, okay? And that is described right here for us, okay? There it is, factor. Here's our x-intercept with the multiplicity. It's time to play Name That Graph, okay? And a little jumping ahead. We look at it. Now it's insisting on coming in. So we got the x-intercepts at -3 and positive 4, which is to suggest we got factors of x plus 3 and x minus 4, product of which is x squared minus 1x minus 12. It also suggests that we're going to get a vertical asymptote here at positive 1, which suggests the x minus 1 is a factor in the denominator. And we're going to take a stab at it, think if that's what it is, and sure enough, okay, factoring the numerator will give us those 2 x-intercepts. Letting x equal 0, we'll pick up 12 as the y-intercept. The division, the long division, should reveal a slant asymptote for us, and we might want to actually figure out what that was, and leave that for you to figure out what that slant asymptote might actually be. Let's look at this expression, okay? Quite interesting. Again, it's going to factor nicely in the numerator, giving us 3x-intercept. It's going to factor in the denominator, giving us 2 vertical asymptotes. We're going to have to do the long division to determine the slant asymptote, and again, we definitely know there's a slant asymptote because of the higher power exceeding the numerator power exceeding the denominator power. That's the dead giveaway of the slant asymptote. So let's take a look at things. This is the graph. Okay, let's see what happens and how we get that. Oh, sorry. I should have actually showed that this was factored. Okay, that when this is factored, you pull out an x. Sorry about that again. All right, we're lost on that one, and I have to pick that one back up first. Okay, here we go. Actually want to show that what these factors are. Okay, then pull out an x, and then you get, I guess, x plus 2, x minus x plus 2, x plus 1. Verticals at the verticals at 3 and -3 vertical asymptotes. And this is a little zoom in on that behavior with around the intercepts, coming up through 0, going through -1, and back up through -2. And yeah, we can cross the slant asymptote. Again, is the end behavior. You can never cross the vertical asymptote because clearly x can never equal 3 or -3. We've said that from the very beginning of the course, because whatever the 3 and -3 causes 0 on the denominator and invokes a restriction on the domain. So, but crossing horizontal asymptotes, crossing slant asymptotes is entirely possible.